Okay, so now I want to go over the next section, which is chapter 10, assignment 10. Now, we've learned 4 things so far. We've learned constant acceleration, forces, energy, and momentum. And then the last chapter, when we went through rotation, we covered 2 of those. We covered constant acceleration and energy. Now, assignment 10, we're going to go back and do some of the same problems over again, but we're going to use forces and we're going to look at momentum right here. So this first section, I'm just going to talk about rotational forces right here. Now, rotational forces, they give it another name for it. They call it a torque. And they use this symbol right here, which is the large letter gamma right there. Now, the definition of the torque is defined as R cross F, where R is the distance. Whenever you take torques, it's about a point or an axis. It's the distance from that point to where the force is. So here, a torque device is just a wrench right here. What do we do with this wrench? We try to turn things right here. Where's the point of root axis? Well, it would be right there at this point, right there. And what the force is the force we apply on it. We usually come over here and we push down on this right here. So in this case right here, it would be the magnitude of R times the magnitude of F. What did we say? It was times the sine of the angle between them. Well, to get maximum torque, you want that to be 1, which means you want that to be 90 degrees. So anytime we try to hit this wrench, we always push with our force perpendicular to our radius. The radius is from here to here. A screwdriver is also a torque device right here. What are you trying to do? You're trying to twist this thing right here. In this case, the radius would just be the radius of this screwdriver right here. You don't get much of a real skinny screwdriver is very tough to get a lot of torque. You want a fat screwdriver right here. It'd be the force you're applying times the radius of this. Okay, if I came, and if I sum up all the torques right here, some of the torques should be just like what we had for, remember we said the sum of the forces was MA. Well, we're just switching letters. Every place we see a force, we replace it with a torque. Every place we saw an M, we replace it with the I. And wherever we see an A, we replace it with alpha. So that's going to be our rotational analog of F equals MA. It's just the sum of the torques equals I alpha. And remember, torques are always about a point right here. So let's look at an example. This thing right here, we have a disc right here, and we just have a rope with a little block tied to it right here. We probably did this problem in assignment 9, and we looked at it with energy, and we just said this potential energy, as it dropped, it all went into the kinetic of this plus the kinetic of that. But now we're going to look at it from a force point of view right there. So what do? We look at the forces on there. Well, we already know the force on this is M, a G. I made them both the same mass. And the tension right here. If we look at the forces on the disc, there's a weight. We draw right through the middle of it. Anytime you're drawing the weight on an extended object, put it right through the center of mass. We have this tension right here. I'm going to call that T prime. And we also have this tension right here. Well, the thing is, so when we take torques, we can't take torques about any point we want. We can only take torques either about the center of mass or about a fixed point. Well, that is the center of mass and it is the fixed point. So that's really the only spot I could possibly take torques around right here. Now, you'll notice any force that goes through that point, I can ignore because the radius, the distance from this force to that point is 0. So any force that's pointing toward that, point P, I can ignore. So the only thing that's causing this to turn, causing this to rotate is the tension right here. So So when we dot this, when we cross this, r cross t, it's the magnitude of r, magnitude of t, times the sine of the angle between them. Well, what's the angle between r and t? That's 90 degrees right here. You notice the direction, when you use the right-hand rule, it's r cross t. It's actually into the board. It's along the axle. It's the only unique line you have right here. So the direction of the torque is actually into the board, but I'm just going to call this direction positive right here, but it's really into the board right here. So when we look at the sum of the torques about that point, all we have is t times r times the sine of the angle between them. That equals I alpha right here. Well, I put in my I. My I was 1/2 mr squared. And my alpha, since there's no slipping, just like we did before when we said v equals r omega, we can say the same thing here. We can say the acceleration of this around is the same as the acceleration of that block going down. So we can turn all of our alphas into a over r's, just like we did with our v's before. Okay, the r's, these r's, and this r all cancel out, and so this equation just simplifies to t equals 1/2 ma. Now we also have the sum of the forces in the y here. I'm calling down positive so that everything works together. We have mg minus t equals ma. So now we have these two equations. Now if I just add them up right here, the t's drop out and we get mg right there. Or I'll just plug in what t is. mg minus 1/2 ma. I just plug t right into it. Equals ma. Put that on the other side. We got 3/2 ma. Cancel the m's, and so a equals 2/3 g. It better be less than g. You certainly, if you cut the rope, it would be g right here. Okay, and now we can get the tension because I can just plug this a back up into here. The 2's drop out and you get 1/3 times the weight right here. So mg better be bigger than t because it's accelerating downward. So t is just 1/3 mg right here. Okay. So let's look at another problem right here. This one over here. You had a problem just like this in chapter 9. The only thing is I'm making the friction 0, but we could have put friction in there. So this is a frictionless right here. And now, here's our rope going over the end. Before, when our pulleys were massless, the tensions were the same, but now they're going to be different. These two tensions are going to be different. Now, if we look at the forces on, we're going to call this direction positive, not positive. We're going to call all the torques going around this way positive, and we're calling down positive. So over here, we've got T1 equals 2ma, because this has a mass of 2m. This one over here, we've got 3mg minus T2 equals 3ma. Now, I don't want to look at forces on this because I don't care about the normal here and the weights. If I look at torques about that point, then the only thing that's causing this to rotate are the two tensions right there. And this tension is the same as that, and this tension is the same as this, but these two are different. If we look at the torques going around this way, we got R times T, because the angle between them is 90, minus, since this is going the other way, this one is minus R times T1, and that equals the I, which is 1/2 mr squared, times alpha, and we remember we just made that A over R right there. Okay, so I can cancel all the R's. One cancels with that, and the other one cancels with these two. So this, remember, we have one more unknown than we used to have because we used to call that the same tension. But we have one more equation, so now we can solve for everything. So here we've got this from our torque, we've got these two from our forces. So I said, well, let's just add this and this and this together. The T1s drop out of here, and the T2s drop out of here when you add them up. So when you add up the whole left side, you just get 3mg. And on the right side, we get a 2ma, a 3ma, and a 1/2 an ma. That's 5.5 MAs or 11.5 MAs. cancel the m's, throw the 2 over on the other side, and you get A equals 6/11 G. Again, better be less than G. Okay, then we can take that A and we can plug it right up into here, and we can get the tension T1. It's just 2m times this, which is 12/11 mg right here. You notice, so there we got T1. Now if we wanted to get T2, we could plug it into this one or into that one right there. I just plugged it into this one, so you got 3 mg minus 3, sorry, I plugged it into here. So we've got T2 equals, sorry, up into here. We got 3 mg minus 3m times A, because I brought this over to this side. So if we bring the A over to this side, A is 6/11 G, and that equals T2. Okay, and then we can just combine these, get a common denominator. That's 33/11 minus, and then this is 18/11, which is 15/11 mg. You'll notice right here, 3 mg is bigger than 15/11 mg because you're accelerating downward right there. Okay, so again, we said torques can only be taken about a fixed point or the center of mass. Now here I just have a ball just rolling down an incline, again, not slipping right here. Now you notice that point is moving right here. This point is moving, but I can take torques about it because it is the center of mass right there. So I can take the torques about that spot. Now, since it's not slipping, there is friction, but the work due to friction is 0 because it's not slipping. Remember, work due to friction is the friction times the distance it slid. And since it doesn't slide, we can say the acceleration of the rim is the same as the acceleration of the center of mass, which is r alpha. And this is static friction, so we can say friction is less than or equal to mu Sn, but we just have an inequality in there. And we know I of a sphere is 2/5 mr squared. So we say it starts from rest right here. And what do we want? I'm going to say, let's find a bunch of stuff. Let's find the acceleration, the angular acceleration, the time it takes to get down, the frictional force. What's the minimum coefficient of friction so it doesn't slide? And what's the speed at the bottom? Okay. Given the angle, the radius, and how far it goes. So, if we look at the sum of the forces in the x, again, I'm putting my coordinate system like this. We got mg sine minus the friction equals ma. We got n minus mg cosine theta, just like we did before, equals 0. But now we have the only thing that's causing this thing to rotate. I don't have to worry about the normal or the mg because it goes right through that point. I only have to worry about the frictional force. So all we have is the friction times the radius, r cross f, equals I alpha. And we know what I is. It's 2/5 mr squared, and it's not slipping, so we can say alpha is A over R. Cancel all the R's, and so now we got the frictional force, which is 2/5 ma. We can take that friction, plug it right back up into here. So we got mg sine theta minus 2/5 ma equals ma, or combine the 2/5 with the 5/5, so we got 7/5, cancel the m's, so A equals 5/7 g sine theta. And we can see that that's definitely a constant, so g's not changing and theta's not changing, so we can use constant acceleration equations. If I wanted to get my alpha, I just need to say alpha is A, that's A over R, so just take that and divide it by R. To get the speed at the bottom, we'll just use this equation. We know it started from rest, and we know what the acceleration is, and we know how far it went. So we'll just come up to here, and we can say v squared, v naught squared was 0, and so all we get is 2a times the distance it moved, which is, remember our a was 5/7, so doubling it, 10/7 gl sine theta. And then take the square root of both sides. We could have gotten this by energy. We could have just said the potential energy here went into both kinetics down there and got it that way too. It's good to know how to do it two ways. If we wanted to get the time down, we'll just use this constant acceleration equation. We know that x is L, x sub naught and v naught were both 0. We plug in our a, t squared, solve for t. Now we've got the time right there. If we wanted to get the frictional force, we already said the frictional force was 2/5 ma. We'll plug in what our a is. Our a was 5/7 g sine theta. The 5's drop out, and you just get 2/7 mg sine theta. Now, the last thing is, if we wanted to get the minimum coefficient of friction, well, friction, remember, is normally less than or equal to, but it's equal when that's at its minimum right there. Well, we know what the friction is, and we know what the normal is. So if we just divide the two, the minimum is the friction divided by a normal. Remember, we said was just mg cosine theta. The mg's drop out, and this is 2/7 tangent theta right here. You notice when we had a block on here, the angle, we could lift this thing all the way up to tangent theta before it started to slide. This one over here is 2/7. We can lift this a lot higher before it'll start to slide. It'll roll, but it won't slide right here. Remember, rolling kind of relieves the pressure on this right here. If I would have put a different shape on here, like a hoop or something, this thing would start to slide at a lower angle because it doesn't give so easily. A sphere gives quite a bit right here. Okay, so this is the first section on torques right here. So your assignment 10, the first side of the sheet will be on torques. The back side is mostly on the momentum part. Okay.